Everybody prepared? I request you 20 minutes minimum, full attention. I hope you are as well prepared as I am. You see, I got a fresh haircut, so you can take pictures. I took my best suit on, proven from my dear wife, so it should look accordingly. And we got as well the presentation up. So next 30 minutes are about hybrid joining in car body. We gave it a look into how do different joining technologies interfere with each other during the joining process as such. But first, a few ideas who we are, who I am. Okay, comes up. So I'm from Atlas Copco, quite a huge group, total group about 46,000 people, roughly 12 billion of sales. The business area I belong to is still remarkably sized, 6,700 employees with 1.6 billion sales. Our division, this is what I directly stand for, is around 1,350 employees. The one of you who likes to know a little more, go to the webpage, there's the annual report and everything. So what are we doing? We have the business area, and the business area covers tightening, adhesive dispensing, self-pierce riveting, and flow drill fastening. So that's the business area. Getting a little closer, the division as such covers the adhesive dispensing, self-pierce riveting, and the flow drill, mainly for car body, not limited. We are as well in battery packs for EVs, but this is the area we will shortly talk about. Dispensing, if you need further details, please join us on our booth. You have all kinds of dispensing in the car body for structures, for sealing, for dampening, for whatever. Can be done in various applications like the swivel on the left-hand side, or here for the epoxy strengthening material. Rivets and riveting machines, so we do the rivets. Likely we are one of the, I would say, biggest supplier for rivets. We can do roughly about 6 billion of rivets per year in 2 locations, in the US and in Europe, and we do the riveting machines as such. And we are as well in the flow drill equipment. So if you have an opportunity to use a flow drill, you are warmly welcome to join us on our booth. Global setup, of course, we are with our dear customers, the OEMs, the car makers, so we have to be where they are, especially where their R&D centers are, as we work very closely with the R&D and the manufacturing engineering. So you see Innovation Center, and this is, so to say, a smart and small add-on. I got a short video clip as well from the Chinese Innovation Center. It's a lab with robots, with everything in. Again, you are welcome. If you have an issue, if you want to test something, contact us. We take it in our lab. We can take complete car bodies in our lab to simulate and test the applications. So much about the company as such. A little bit about our, we call it technology network. As you might know, you can never do this by yourself. Not everything you can do. So we have set up a nice technology network. I start from the top left. Sperea is a Scandinavian institute. We cooperate intensively on the field of hybrid joining. Hybrid joining in car body, likely you will see the Volvos and the Scanias and all these OEMs. We have a nice setup with Fraunhofer and Chemnitz, as they are known to be one of the leading institutes in thermal joining technologies. resistance, spot weld, arc weld, laser weld, etc. In Dresden is a major hub for mechanical joining. Mechanical joining such as self-pierce rivets and flow drills and clinch. With Flanders Make, this is newly set up, fairly unknown, very small institute in Belgium. But the good thing is, these guys are very close to the proving ground of Ford. And Ford rents the proving ground as well to other OEMs. So you see major European OEMs testing their cars on the proving ground, take them into Flanders Make's climate chamber to run the car under proving ground conditions, but different environmental conditions, such as minus 30 degrees. How does my EV behave under minus 30 or plus 60 degrees? Now this one we have skipped. Warwick is important for us for the simulation of mechanical joining. So as you can imagine, simulation takes place. It's more and more getting important. And the Warwick University supports us in developing the necessary models and tools to simulate our mechanical joining. University Dresden has to be seen with the Fraunhofer. Also they are important for mechanical joining. They are known especially for fasteners, for flow drills and normal fasteners. And we did a nice study on so-called laser riveting. Auto Steel in US, a DLR, is a European aerospace stuff, the ones that create the Ariane. And likely these people know very well about lightweight. So what we do with them is we create our internal training, how cars are built. We discuss with them about new ideas in lightweighting and the respective joining technologies. RRT, a French institute, if you want to work with Renault Nissan Group now, or with Peugeot, PSA, there is no way around. You have to cooperate with IRT because these two OEMs, they outsource most of their R&D work to this institute. Vincent Network, to mention, Arnold for the fasteners, steering for welding, Quiz. Quiz is also very important for the quality check and quality verification. You see, we are not alone. We have set this up to strengthen our know-how and improve our joining technologies in-house. Now to the topic, what is hybrid joining? Hybrid joining, very simply, is when you combine two or more joining technologies. Mostly, we talk about adhesive with a mechanical or a thermal joining. So, if you are, as OEM, if you weld your car body and you use at the same time adhesive, it's already called a hybrid joining. Mostly you see this in the spot weld, in the flow drill and in self-pierce rivets. A little less on laser, but we will focus on that later on. Why? So why should you do something complicated if it's also possible to do it simple? There are three main reasons to remember. One, you can double or triple the strength, there is no doubt. A hybrid joint increases the strength significantly. Number two, corrosion. And number three is the overall stiffness and the drive feeling. So if you drive a car that's only spot welded and you take the same car and you add structural adhesive, you will significantly feel that it drives more accurate and precisely. There is less twisting and turning in that car. Three main topics why we use hybrid joining in the industry. I'm sure you will find a few more, but we selected these ones to be the most important. So where? It's basically all over. It can be in the hand flange, it can be with self-pierce rivets, with spot welds, with flow drills, and even in a battery pack you have hybrid joints. Most of you might not realize, but in a battery pack, there is a lot of adhesive, there is a lot of gap filler, of heat transfer paste, and this goes together with fasteners, and these fasteners cannot be operated like it has been done before in a traditional powertrain. I will explain this, why this is different, and you need to consider hybrid joining there. So, first one, spot weld. Spot weld is very common, everybody knows it. So that's not really a miracle anymore. But if you give a closer look, without being too scientific, if you give a closer look, you see here a difference. Now let's see if this laser doesn't really work. I take my hands. So this blue is without adhesive, and the red one is with adhesive. And you will see, if you take the same parameters, if you take the same sample, the same coupon, you will see that your adaptive weld controller has to adapt to this isolating adhesive. There is no doubt. If you don't do this, your welds will not be the same. In other words, you definitely need a different parameter to weld with adhesive than you need without adhesive. So, a strong recommendation here, consider adaptive weld controllers if you are going to be challenged with a hybrid joint on spot weld. But we did as well a more, let's say, scientific study. And what you see here, you see nothing because it doesn't work. You should actually see, let me check if it starts when we push the button again. No. Can we try to manually start the videos, please? And the other one as well. Now, this is it's going to work or not. See, I got your attention even so it doesn't work. That's not nice. Actually, this should be a video as an X-ray CT scan through the joint. So instead of taking cut sections, we send this sample through an X-ray machine, to a CT scan machine, and the result is very clear. Whether we do an adhesive application like this, where we do no adhesive in the spot weld, or the traditional way, adhesive all over, we get the same zone, the same diameter around the weld nugget where physically all adhesive is gone. It's burned away. And you got fuel, and that's it. So then the question is, why the hell should we do adhesive, spend money, and then burn it away and spend another portion of money for a nice exhaust system with filter? The better way definitely is to save this, to use a so-called stitch speed. And I got a number from Audi that has been dropped officially during another session. They saved 1.1 million euros on the Audi A3 cycling running in one plant on one line. So this is not a global number, this is a local number from Ingolstadt. I mean, that's a significant number. And Honda also has changed to stitch speed, but they don't tell us the savings. They say they wouldn't do it and spend the extra money for stitch speed if there would not be, on the other hand, a significant money saving. So I'm sorry about the video. Normally you should see this very clear. You can typically say, if you want to reach, let's say, a 5mm weld nugget, there is a zone around the weld nugget of 10mm, which is completely free of any adhesive because the heat was so enormous that it burns away. The next technology we looked into is the flow drill. On the flow drill, you can hardly see something as a difference, except here. Again, the red is with, and the blue is without adhesive. When you get through the top layer, the adhesive for a very short moment acts as a kind of lubricant. So the torque is a little less than before. If you would have the same parameters, your controller will say, oh, something wrong. So you have to adjust your parameters according and your tolerance bandwidth. But besides this, there are two more significance if you run flow drill with adhesive. And let's see if this video operates. Yep, lucky, we are lucky. So again, the same concept. We took a sample, a coupon, and we sent it through. And what you see in the middle here, you create a bigger gap between the two sheets. In this case, this is no pre-hole. So we really went through the top layer into the second layer. But you physically create a volume, and this volume cannot really be filled completely with adhesive. You have to be aware about that. So less speed, less axial power is beneficial for the process. But what you also see, if you have a pre-hole, these are, by the way, the rest of our samples, if you have a pre-hole, you create significant squeeze out. And this can contaminate your fastener's head. Also, for that, we recommend strongly a kind of regulated bead. Do not use excessive bead, excessive material. You will create excessive squeeze out, and this can create an issue with your device. Now let's look into the self-pierce riveting. As you might be aware, self-pierce riveting uses by far higher forces to punch the rivet in than we have on a spot weld or on a flow drill. Physically, you squeeze away most of the adhesive. This is like you would hammer on a nice adhesive bead. Where you hammer on it, it's gone. So, on the other hand, it's a very robust process. The process as such doesn't care whether there is adhesive or not. The results and the parameters are mostly the same. But what actually happens, also here is a short video, please. Yep, should come. Also, this is a cut section, and what you nicely see, the gap between the sheets is close to zero, naturally. 50 to 60 or even 80 kilonewtons on a 5mm rivet. There cannot be any gap anymore. With that, there's no adhesive anymore. And this, if we go to the next page, yep. It says confidential, of course, clear. I explained the result, but not how we did it. This is the confidential point. This, what you see on the left hand, this happens if you have a flange, you apply your adhesive, you set your rivet. Okay? You squeeze away the adhesive, and of course it has to go somewhere. It's not like on a weld spot where you burn it away and it's gone. Here, on the right hand side, you see that we get a quilting. In other words, it's blowing the sheets up between the rivets. In that case, in our sample, where we had the 1.5 mil in the upper and the 3 mil in the lower, it's 0.67 mil of quilting. With an improved process on the adhesive, doing the same sheets, everything's the same rivet, everything's the same. Just the process different. If you peel it off, you see that the layer is by far more equal, and you get a nice result on the quilting. It's much better, it's much improved. This is the recommendation. Don't do a normal bead and expect that this will work 100% proper. It will not work that proper. There are ways to improve it. I can't just tell you yet, because we are in a pattern process, how we do it. Finally, before we go to the battery packs, let's look on laser. Who is on laser welding? Anybody here? A lot of cameras, but no laser welders, okay. Naturally, our experience, it's either laser welding or it is adhesive. For whatever reason, engineers stay away from adhesive if they have to laser weld, and vice versa. We wanted to understand why. So why the heck is there no combination? Because there are obvious advantages in combining these two. What we have done, we took a coupon, we apply adhesive here, we leave a space, and we apply adhesive here. And then we take it into a laser weld gun, simply to make our life easy. There is no fixture needed, no safety protection needed. The laser gun is, so to say, sealing itself because it's closing like a spot weld gun. You see this here on the lower. You've got the adhesive here, and this is the area where you finally have the laser doing the laser weld. So, looking on that, first result, nothing works without a gap. Laser welding, you definitely need the gap to let the gas go out, especially if you have a coated steel material, which we had. So this is a standard steel, a mild steel. Everybody of you is using this kind of steel, especially for closures or side panels, where you need a good formability. The trick is, we filled the adhesive with glass balls. Glass balls are widely used, maybe you don't know it, but there's a lot of applications where the supplier for adhesive, the chemical companies, they fill in glass balls with a diameter of roughly 150 micron. This helps to make an equal and repeatable thickness of the adhesive. The performance of adhesive is in an absolute function of the thickness of the layer. If it's too thin, you will not get the performance. If it's too thick, it will not get hardened. So to have an equal, predictable and repeatable thickness is essential. In that case, we use the glass balls as well to create a predictable displacement, so to say. And we found that the glass balls also giving us the necessary gap between the sheets to let the gas go out when we laser weld. We know from OEMs that they make small dimples to give this, but you can as well use the glass balls to do it. The second result, to our surprise, quickly go back. The first samples, we made a very short laser weld here that did not touch the adhesive. Then we made other samples where we got to the edge of the adhesive, and then another batch where we welded a little bit into the adhesive. And to our surprise, the process is relatively robust. In other words, as long as you are not welding excessively into the adhesive, it works. A few millimeters plus minus is tolerable. So the message here is, it can be done, it's physically possible, the machines are out, use glass balls, and use a precise enough laser weld and adhesive equipment, then you can do it, and then you also can gain out the advantage. As you see here, we made as well, of course, pull tests. The laser only is the blue, the green one. The adhesive only is the blue one, and the combination naturally, as expected, performs much better, which is the red one. Well, let's leave the car body and make a move into batteries. I took a short clip from the internet. It's a courtesy from GM, by the way. What you see has been done from LG, but it's designed and engineered from GM. I show this in order to make you aware that this is high-tech. This is not just buying a few batteries and putting in a box and a few cables. What you definitely need is a real good temperature conditioning system. Otherwise you cannot charge and do the fast charging, and also the discharging is under risk. This is maybe a little over-engineered, but I show it because here we have for each cell a temperature sensor and a conditioning system. And between each of these we get significant amount of adhesive. Now if you are in the business, a battery is breathing like we human beings. Yeah? And your volume is increasing, and when it's getting less. The same happens here. You cannot just screw it together and think this will work. This is going to breathe a few millimeters. You have to give this room. And that's why they put adhesive and the seals and everything in between. Yeah, we can, I think, get a little further. This is a simulation where you find adhesive applications. You got the cells. Some companies really glue the cells to each other. Others have a different philosophy, but Chinese like this technology I've seen. So they glue the cells to each other. Then you need heat transfer paste to get the heat out of these battery cells. You have to box it. Think about this needs to breathe, so don't use a metric 10 rod and get to the last torque. And then this one as well needs to go into a box where you have the heat transfer paste again. So here we talk hybrid joining, namely adhesive and fastening. How to do it? Giving you a real example. We have the seal cover as above. We have a gap filler here, which is actually a picture taken from the Mercedes. So you see there's a gap filler and you put the tray on it. What you need to do, you have to let this material flow. In other words, like in a cylinder head or a gearbox housing, to just fasten your bolt or your nut, one shot, done, doesn't work. These materials are highly thixotropic. The harder you push, the harder they get. So what the recommendation is, take at least a two-step approach or even a multi-step approach. Start very soft, squeeze it away under a low speed so it can really flow without problem. Wait, and then perform the step number 2. And maybe even a step number 3 needed, depending on the amount of material. That needs to be considered in the cycle time. It's not that much a problem of technology. Software is there. but you need to know this in your process time, because suddenly you need 3 to 4 times more process time than you are used to do. Okay. By the way, this is only for information. We are monitoring this industry quite in detail. We have our own dashboard, which is monthly updated, who does what and who cares for what and who delivers to whom, and the concepts and the chemistry that goes inside. Everything that's needed to monitor this business. Now I promised you a small add-on. On the left-hand side, you see the innovation center we have in China. So again, you are warmly welcome. Get your issues, get your tasks, challenge us, get this to us, and we will make a test and tell you under what conditions this job can be done. So we have the adhesive, we have the flow drill, and we have the rivet under one roof. And the fastening, by the way, we can do as well. So we can as well check out how many steps you need to fix your battery or any other item. So on the right-hand side, this is the newly set up innovation center in Europe. It's a little bit bigger than in China. Same concept. We got the robots, we got all the processes, and we invite all the OEMs to do the test in-house. This time we even had a 6-step battery assembly as a showcase. So finally, you can picture this if you have questions. Send me an SMS or send me an email. You can as well go to the booth to my colleagues. Any questions? No questions? I have been part of SCA, so this is a few years ago already.
Oliver Paul, Mitglieder Jung, just a curiosity question because I know SCA Stuttgart 20 years ago, and I didn't know that Atlas Copco bought it.
Yeah, you are right. We kept this a little, let's say, behind the scenes quite a long time. So the name, the company did exist almost 5 years before we finally transferred everything into Atlas Copco. But that has to do with the long-term strategy. Now it's the adhesive, it is the riveting, it is the flow drill, it is question. And then you need one big umbrella. You cannot do this under the roof of SCA anymore. Good. Thank you very much.